Hey, what's going on, guys? Stefan from App Stuff. Welcome back. In this video, we're going to be finishing up our binary search tree series, and we're going to be going over two things: removing a node and traversing through a tree. And we're going to start out with how to remove a node from our binary search tree. So there are going to be three different cases. There's going to be one where the node has no children, or it's a leaf. There's going to be where the node has one child, and this presents a slight challenge because the node that we remove, if it has one child, it has to be replaced. So we see if we remove 18, we're going to connect 5 to this node here, and this was what the tree will become. And the most difficult case is removing a node with 2 children. So what we're going to be doing is basically what this is saying is this tree could be restructured by taking the minimum value of the right side of the tree and putting it up here where this 5 is, and then restructuring the tree in this way. So what we're going to be doing is when we run into the case where the node we want to remove has 2 children, we are going to be finding the minimum value of the right side of that node and then using that value to replace the value that's being deleted. So if we want to remove 12, we get 19, and we connect 5 to 19 and then remove that 19 value. So the tree would then look like this. Okay, so let's go ahead and get started with the code. And before we do that, I want to change up this description method we have here. I found a better way of representing this tree. So just go ahead and let's do this. So cut that out. We're going to say result plus equals left.description, and then result plus equals this guy, and it's going to be a closed parenthesis and a pointer to the left, and this guy is just going to be an open parenthesis. And we're going to do the same thing for the right. And the reason I didn't do this before, guys, is because Xcode has a bug in the version that I'm using. So if we try to do this, for some reason it won't allow us to put parentheses around that string, and the program doesn't compile. So we're going to go ahead and do this for the right side as well. And basically this is just going to wrap everything in parentheses and make it easier for us to read what's going on in our tree. So we're going to do this. Okay, so let's print out our tree now and see if this is working correctly. So what's our root node? Our root node is 8. We actually need a space there. Okay. So now we see that our root node is 8, and then our 10 is the only right node that we have, and then 6 is the next node, and then 6 has a right node of 7 and a left node of 4. So this makes things a lot more easy to read and understand. So now let's go ahead and get into our node removal. So we're going to say extension binary search tree, and we're going to write a function called remove, and we're going to remove by value. And there's going to be 3 cases, right? We're going to say is leaf has 1 child, has 2 children. So let's go ahead and get started with this. We're basically going to say if, well, first what we need to do is find our tree that we are removing. So we're going to say guard let tree equal search and return tree for value else return. And if you guys remember, this finds the tree that we want, and it makes sure that the value exists, and then gives us back the associated tree that we are looking for. So for example, if we wanted to delete 12, and that function is going to, when we search for 12, it's going to give us back the tree associated with 12. So 12 would be the root value, then 9, 21, 19, 25. So that's what that does. Now we're going to say if that tree is a leaf, then we're going to write a function to remove that leaf tree. So let's go ahead, and this is going to be a helper function, so make it private. We're going to say remove leaf, and we're going to pass in a tree, which is going to be a binary search tree. And I forgot to say func. Okay, guys, so let's look at this case over here. So we need to determine whether or not the tree is a left node or a right node, because when we remove it, we're going to say, okay, make the parent value the left side, make that nil, or if it was right, we would do the opposite. So what we're going to need is some more Boolean variables. Right now we have one for isLeaf. We're going to need one for isLeft and isRight. So we're going to say var isLeft bool. And if we remember from the conditions of our binary search tree, a node is a left node if its parent value is if its value is less than its parent value, right? So we're going to say return value is less than parent dot value, and we have to force unwrap that parent there. But we always know it's going to be there if we've inserted this this node, right? So, and then we're going to say var isRight bool, and then we're going to say return value is greater than parent dot value. Oops. Actually, do we have to force unwrap that? Let me see if we get an error here. Yeah. So you'll see there. Or we could just do like we did before. Okay, so that's our isRight and isLeft conditions, guys. So let's hop back down to our function. And we're going to say if tree dot isLeft, and then we can actually just say else. We're going to say tree dot parent dot left equals nil, and for the right we're just going to say right equals nil, and that's all we have to do to remove our leaf. And then make sure that you call that function up there under your isLeaf condition, and let's go ahead and test it out. So if we print our tree, let's go ahead and see if we can remove 7, which is a leaf node. So we're going to say tree.remove 7, and then let's print our tree out again. Okay. And we notice that 7 is now gone. It's just 6 and 4. All right. And then if we want to remove 4, print tree, 6 will just be by itself. We get 8, 6, and 10. So that's working there really nicely, guys. So I'll just go over really briefly what we just did. So we're asking our program, or this remove function, if the tree we're trying to remove is a leaf, and that tree is the tree that we get back when we do this search and return tree function that we did in part 1. So that tree right now is just going to give us back, say we were trying to remove 7, it's just going to give us back the tree of 7. And then we're going down here and we're saying if tree is left, no it's not, 7 was on the right side. So it's going to say tree.parent.right equals nil. So the 7's parent was 6, and then we're setting the right value, which was 7, to nil in order to delete it. So that's what was going on there. And now we are going to write our function out to remove a node with one child. So func remove node with one child, tree, binary search tree. Okay, and let's go back and look at, oops, wrong one. This guy here. Okay, so we again need to determine if it's a left or right node and if it has one child or 2, right? So let's go ahead and do that first. So we're going to say var has one child, bool, and then we're just going to return left is not equal to nil, or right is not equal to nil. If you guys don't understand the and or the or, this is basically going to return true if one of these is valid, essentially. So if this will only return false if both of these conditions are not met. But if one of them is, this has one child, Boolean variable will return true. So let's go ahead and go back down to our function, remove node with one child, and we're going to say, sorry, this guy, if tree dot has one child, then we're going to say remove node with one child and pass in our tree. So now let's go ahead and get started with the code for removing that child from our tree and replacing it with a new value or a new tree. Okay, so first we're going to need to determine if the tree is a left node or a right node. So we're going to say if tree dot is left, and then we can just say else, and let's get some space going here. Okay, so if we hop back over to this guy, we need to determine if it's a left or a right node, because we're going to be if it's a right node, we're going to say parent.right is then equal to this guy down here. Now we also need to do a little bit more logic. We need to determine if this node here has a left node or a right node, right? So we're going to be writing some variables to do that as well. So let's go back over here and hop back up to our class declaration and make two more Boolean variables called has left and has right. So this is just going to be pretty simple. It's going to return left is not equal to nil, and var has right bool return right is not equal to nil. Okay guys, so let's hop back down into our function. And now we need to say, okay, if tree dot has right, or you can, I like to start with left, and then we can say else, and if tree dot has right, and then we can also say else down there. Sorry, left, my bad. Okay, so now let's handle the case for what we see in this example here, and then we'll fill out the rest. So this tree has a right node, so then we're going to say tree the tree dot parent dot right is equal to this tree's right node. Okay, so it's that simple. So we're going to be in this else block here because it's a left. Sorry, it's a right tree, and then it doesn't have a left; it has a right. So we're going to say tree dot parent dot right is equal to tree dot right. Okay, and for the left, we just do the opposite. So tree dot parent dot right, oops, equals tree dot left. Right, and it's because we say right both times here because this is on the right side of our tree. So let's actually go down here and see if we get the correct output. So I changed up our values, guys, to match that of this example tree we see here. So we can determine if we're getting back the correct values based on that example. So you can pause the video and go ahead and do that. I'm going to print this tree, and I'm only doing the right side. So it goes 5, 18, 21, 19, 25. Now let's remove 18 and see if it gets replaced with the correct node. So we're going to say tree.remove value 18 and print out our tree again. And that's looking good. It got replaced with 21, and it's still 21 has a left node of 19 and the right node of 25, right? And that's what we see here: 5, 21, 19, 25. So that's looking good, guys. Now let's go ahead and fill out the rest of our code. So it's just going to be the opposite. We're going to say tree.parent.left equals tree.left, and tree.parent.left equals tree.right. And I'm pretty sure that works. You guys can go ahead and test it out. I'm not going to, because for the sake of time, we need to get into removing a node with 2 children, and this is a pretty complicated case, so it's going to take a little bit of time for us to get done. So remove node with 2 children, tree, binary search tree. Okay, so let's go back up here. And we need to say if tree.has 2 children, and we need to create this variable, right? Because that's where we're going to call that helper function. So go all the way back up, say var has 2 children, bool, and then how this was one or the other, this needs to be one and the other. So we're going to say return left is not equal to nil, and right is not equal to nil. So again, for those of you who aren't familiar with this logic structure, the and symbol, in order for this to return true, both of these conditions have to be met. If it's false, only one of these conditions have to be false. So, okay, so let's hop back down to our function here, and let's make sure we call it. So we're going to say tree.remove node with 2 children and pass in our tree. And let's go ahead and get started with the code. But before we do that, I did find a better example than the one we were looking at previously, because when I was doing the code and I was running through some test cases, I found an error with my code, and having these 2 cases helped me solve that. So essentially, when we are deleting this node, it's a slightly different because its child nodes have more child nodes, right? So this is like a grandfather node, and we're replacing this node with a value that's farther down. This node also has two nodes, but those nodes have no children. So to me, the logic was a little different. There might be a way to kind of wrap everything up in one method, but um, we're going to be using this example to go off of in our code. So I actually got all those numbers down in here, and then that's what it's going to look like down here. So we have 7 as our root. It goes down to 2. Then 2 has a left node of 1. It also has a right node of 4, and then 4 has 3 and 5 as its two children, right? So, and if you guys remember, we need to replace the node with the rightmost minimum value. So that's what this is going to look like. We're going to say guard let tree equals search and return tree for value, and we're going to say tree.right.minimum else return. And instead of returning just an integer value with this minimum guy, we actually need to go back up here and tell it to return a binary search tree. And same with our maximum. So binary search tree and this guy. Okay. So that's all we need to do there. And now let's actually let's see. Oh, dot value, right? So now let's go ahead and just print out this tree and see what we get back. So go down here and just type out tree.remove value and say 4. Four. Yeah, that's the one we want to remove. Let's see. Got an error there, and just do this. Okay. So now we can go ahead and say tree.remove value 4. Okay, and it gives us back 5, which is what we want, right? Because that is the smallest value on the right-hand side. So now that we have that tree that we're going to be removing, we need to say if tree.isLeft and else, right? Because we need to determine if the tree, which is 4, is a left node or a right node. In this case, it's a right node, right? Sorry, we need to call this replacement tree. And this is the tree that we're looking at. In this case, it would be 4. So let me go back down here and print out our tree so we can have a good representation of this stuff. Okay, so we want to remove 4, and 4 is a right node because it's on the right side of 2, right? And then our replacement tree is going to be 5. Okay, guys, so really quick, here's the logic, right? We're going to say if the replacement tree's parent value, which is 4, is equal to the same value of the tree that we're deleting, which in this case is also 4, then we're just going to move 5 up and then make the left node of 5 to be that guy and take that guy out. So it's different in this case when the node that we are deleting has more children, right? Because the replacement node has another parent and it's not the node we are deleting. So we need to handle the logic for both cases. So it's pretty easy. It's going to be if replacement tree, which is 5.parent.value, which in this case is 4, is equal to the tree we are looking at to delete, which is the tree of 4. Then what do we want to do? We want to say, let's see. We want to say the original tree's parent right value is now 5, and then 5 needs to connect to 3. So we're going to say tree.parent.right is equal to replacement tree, and then we're going to say replacement tree.left is equal to tree.left, right? So if we were to run this code right now, we should be getting back the proper tree where 5 takes that place, right? So let's go ahead and look at that. We're going to say tree.remove value 4, and hopefully this works. And we need to print our tree again, sorry. Okay, so let's see. It goes 7 down to 2, with 2 goes to 1, and then now 2 is going to 5, which is going to 3. So that is working perfectly. Now we need to handle the case for the left side of this, right? So we're going to go up and just copy this, and the logic is just going to be a little bit different. So really quick, guys, we can just imagine that if there were two nodes here instead, we would move this right one up. So it would be now the parent tree dot left would be equal to this guy, and then this line of code would be the same. We're connecting the replacement tree to the left side, so, or that left node. So here we're just going to say right there. We're going to say left instead. Okay, sorry that took me a second. So it would be tree.parent.left equals replace. Okay, yeah, that's looking perfect. Okay, so now let's cover our else case, right? On each side. All right, so this is going to be the case for when we have to go further down our tree, right? So the logic is going to be, we want to go find the minimum value on the right, which we've already done, and then we are going to take that value and place it there. So let's see what we need to do. We need to say this replacement tree has the right side of this original tree and the left side of this original tree. So let's go ahead and do that. We're going to now say replacement tree dot right equals tree dot right, and replacement tree dot left equals tree dot left. And then we also need to make this value nil, right? So we need to remove that 11 there. So we're going to say replacement tree dot parent dot left is equal to nil. So we're going to say replacement tree dot parent dot left equals nil. And that should be it for the logic, guys. Let's go ahead and see if this works. So let's see if we can remove 10 and have it be replaced by 11. So boom. And it's causing an error because it's taking a lot of time to compile. So there's something we need to switch around here, guys, and it's actually going to be the order in which we call these functions, right? So this is a little tricky. We're going to want to put this guy first, and then at the end of this statement type return, okay? And then we're going to want to put this guy second, and at the end of that statement type return. Okay, because essentially what was happening, guys, is that when we were going through that control flow, remember that has one child block of code was getting hit because it has two children, but it has one child also holds true. So we need to check if it has two children first. If it does, call the correct function and then return out of this function so that code down there doesn't run. So I'm pretty sure that's what the error was. Let's go ahead and run this again and see if that was the case. Okay, and if you guys were to run that code right now, it actually wouldn't work. So let's go back up here, and we actually need to put this guy up here first. So essentially, we are setting this node equal to nil first, and then we then set the replacement tree right side and left side to the original tree's right and left side, and then we need to reconnect the parent node to the replacement tree. So we're going to say tree.parent.left is equal to, because remember this node's on the right side, so it's going to be tree.parent.right. Yep, tree.parent.right is equal to replacement tree. Okay, so that's going to be all we need to do there, guys, and this should now work. Okay, so I had to add in 8 there. I don't think I had that in there before. So you're going to notice that 11 now becomes the replacement node for 10. So it goes 7, 11, 8, 9, and then 11 down to 12 and 13. And that's exactly what we see here. 11 down to 8, and then 9, and then 12 and 13. So that's looking really good. And now all we need to do is copy and paste this stuff and do it for the left side, right? So instead of left, it's going to be, actually, no, that's going to remain the same, right? These 3 lines of code actually stay the same. But instead now we're going to say tree.parent.left equals replacement tree. So that's all the logic that we have to change there. Because remember, the node we're replacing is always going to be the leftmost node on the right-hand side of the tree, right? So if it was like down here, if we were replacing 2 it would get replaced with 3. So let's actually go ahead and give that a try and see if it works. So let's say 2, print our tree, and yep, we noticed that 3 is the value it's getting, that's replacing 2, and it goes 7 down to 3 down to 1 and then over to 4 and then over to 5. So that's looking really good there, guys. I know that was a lot. It's pretty intense, and it's like a complicated thing with a lot of logic. I hope you guys understand it. But I'm gonna stop there with our node removal, and we're gonna move on to tree traversal. So let's go ahead and hop over here and go to this page so we can understand what that is, and then we will be done with binary search trees. Thank God. Okay. Okay, guys, so save the easiest thing for last. This is tree traversal. It's basically just how we're going to iterate through our tree, or how to read the tree in different ways, essentially. Trees are unique because they're not linear data structures like arrays where there's only one way to read through them or iterate through them. So we're going to have in order, pre-order, and post-order traversal. And in order is going to look like this. We're going to go left, root, then right. So it's going to go 4, 2, 5, 1, 3. And this isn't a binary search tree, but the logic for the traversal remains the same. So let's go ahead and write out these functions now. So we are going to say extension binary search tree, and we're going to write a func for in order traversal, and it's going to return an array of integers. That's how we're going to represent this stuff. We're going to say var result equals an array of integers. Actually, it's going to be easier if we do this. Go ahead and copy this and paste it 2 more times. We'll say pre and post. Okay, now what we're going to do is say var result equals an empty array of integers, and then we'll return the result. And this is going to be left, root, right. This one is going to be, let's see, pre-order is root left, right, root left, right, and this guy is right, left, root. Okay, so this is going to be really easy, guys. It's essentially the same thing as how we printed out our tree here. And in order traversal is going to be the exact same method. So we're going to say if let left equals left, and then we're going to say results plus equals left dot description. Then we're going to append the root, and so for that we are going to say result dot append, not description dot in order traversal, sorry. And then we're going to append the value, the self dot value, which is the root node value, and then the right side. So we can just go ahead and copy and paste this, right, right, and right. Okay, so let's go down here and see what this is going to look like. Before we can run this, we actually need to say get our return values here. And just go ahead and do this here. Okay, so now we can just say print tree dot in order traversal. Boom. What are you doing? Okay, let's go, and we should be good to go now. And it gives us that stuff in the correct order, which is looking good. Now we're just going to copy and paste all this stuff, guys. It's just going to be done in a different order. So we're going to say result.append self.value, and then we are going to go to the left side and then to the right side, and that is going to be all we need to do for pre-order traversal. And this is going to be right, left, root. So just go ahead. That's it, guys. So now we're going to say print tree dot pre-order traversal and print tree dot post order traversal. And actually, before we run that, we need to change these recursive methods here. So go ahead and do this. boom, boom, and post order traversal, boom, boom. And now go ahead and run this, and you guys can double check this stuff. I'm not going to because I know it's right. And that's essentially all you need to do for traversal, guys. It's very simple. And that's going to wrap it up for our binary search tree series. We covered a lot of stuff. I'm going to go over everything we did in part one really quickly just because I promised that. If you feel like you're good to go on it and don't need that explanation, feel free to cut it off here. Don't forget to hit the subscribe button if you want to see more videos like this. I'm going to be doing a lot more algorithms. I'm also going to include series on a lot of cool Swift tricks. I'm going to be building some cool apps, so make sure you subscribe to the channel. It's new and there's a lot of material to come if you guys like the way I code. So let's go ahead and start at the top. So this is our class declaration. And we declared a couple properties. Every tree needs a value. That's why it's not optional, because every tree has to have a value. This is where we initialize our tree with that value. And then every tree has to have a left, a right, or sorry, not every tree has to have these values. That's why they're optional. But every tree needs to be able to have a left, a right, and a parent, right? And all of those values or nodes need to also be binary search trees. So that's what we did there. All of these properties here are just little logic checks to determine properties of our trees. Is it a leaf node, left node, right node? Does it have a left? Does it have a right? Does it have one child or have two children? The logic there is all pretty self-explanatory and simple. This was our first function that we wrote for this class, and it's to insert values into our tree. And if you guys remember, the requirements for inserting a value into our tree are that left values that are smaller than the tree we're inserting to have to go on the left, values that are bigger go on the right. So that's where we start our logic out as. So when we're inserting a value, we say, is it less than our self.value? And self refers to the parent node or the root node. And then here we're going to check to see if a node exists or not on the left side. So in this case, let's go back to this example. We start with 7, right? And then we insert 2. And that function is going to say, okay, 2 is less than 7, so we know it goes on the left side. And then it's going to say, does 7 have a left node already? It's going to say no. So then it's going to hit this little else block, and it's going to create that left node, and it's going to be a binary search tree. And then it's going to say left.parent equals self, which in this case would be 7. And then say when we want to insert 1, it's going to hit this if block, right? Because this if left condition is going to be met. So because that left node exists, this is the same thing as saying if the left is not equal to nil, then store that left node in this value. So then we're going to call left.insert. So this is the first time we saw some recursion. So it's going to say, it's going to go back and run through this function again and perform all this logic again. And we were trying to insert 1. So this is what it's going to look like. It says, okay, we have a left node now. And when we call that function again, it's going to say, is 1 less than or greater to 2? We're not looking at 7 anymore because we called insert off of our left tree, which is 2. And it's going to say, okay, 1 is less than 2, so it goes on the left side. And then it's going to, 2 does not currently have a node on the left, so it's going to hit this else block, and then it's going to create 1 as a new node and declare 2 as the parent of 1. And the same logic holds true for the right side, right? So that's what our inserting was. Oh, and then we created this function here so that we didn't have to set the parent every time because it's always going to be equal to self. Like when we call left.insert, the parent is going to be equal to whatever the left node was. In the case we just looked at, it was 2. And that's why we did that there. So our insert functionality is easier on us. Then we looked at this search and return tree and search for value method, right? So this is what this stuff involves. So this is the method we wrote first, and it basically just returns a Boolean variable telling us whether or not our value exists in that tree. And we use this very similar method of recursion in order to accomplish that. And this is the exact same thing, but instead it's going to return a binary search tree. So the difference is one method, and we really only need this method. I just kept them both here so you guys could see like the difference in return methods. But say we were looking for 10. The first method is just going to say we found 10, so our search is successful. The second method is going to return the tree that is going to return 10 and all of the associated nodes with 10 as far as its children go. So that was really useful in some other functions that we wrote, and I'll explain why once we get to them. So essentially we search for 10 and gives us back this tree here, 10, 8, 9, 10, 12, 11, 13. So that's what these functions were doing. And I'm not going to explain the recursion just because I don't want to beat a dead horse here. If you guys need more help with that, you can just Google it, and there's tons of cool examples there out there on the internet. So now let's get into these minimum, maximum, height, and depth functions. These are pretty cool because they use some pretty neat programming tricks. So, or the way we found the solutions was just pretty elegant in my opinion. So we created this variable that kept track of whatever node is the self. In this case, we start at 7. And to find the minimum value, we want to go all the way down to 1, right? So we're just saying while the left node is not equal to nil, let's reset that node every time we hit a left node until we no longer have any more left nodes. And then we're just going to return that guy there. Same for the maximum. The height was a little confusing. It's essentially just using some recursion to determine the height of our tree, how far down it goes. It's going to return 1 plus the max of the left dot height and the right dot height. So we're using some more recursion there. And it's essentially just going to keep running through this recursively until it gets to a leaf and it returns 0. And then it's just going to return 1 plus all of those values to give us, or 1 plus 1 plus 1, however many times, to give us the height of our tree. The depth function was pretty cool. And this is the last thing I'm going to explain, guys, because I just did everything else is done in part 2. So essentially, we use that search and return tree function here. And so when we're looking for the depth of a node, we say we're looking for 10, or let's do 8, right? It's going to go ahead and find 8, and then it's going to give us back that tree, so 8 and 9. And what we're doing is we're just going to count up until we reach our parent node. And we know we've reached our parent node when our node no longer has a parent. So that's our root node, right? So we're going to find it, and then we're going to say while the node's parent is not equal to nil, increment me 1 each time, and then set the node we are looking at. So it's going to go from 8 to 10, and then from 10 to 7, and then it knows to stop once the node equals 7, and our count would be 2. So that's the depth function there. So we're essentially counting upward until we run out of parents, and then incrementing our depth by 1 each time we do that to return our depth. So that's going to be it for the overview, guys. I went into a lot of detail on this node removal and the tree traversal and stuff in this video. I hope you guys liked it. If you are still confused, feel free to send me some questions or just do some Googling. To get better at this stuff, I recommend trying to recreate this whole thing on your own, and looking at where you're finding your weak spots, which is going to be like, okay, I've run into something I can't figure out without looking at the answer. And then keep on doing that until you can really get through the whole thing without having to look at the completed source code. And try to make sure you're not just doing it off memory. Try to make sure you actually understand what's going on. So that's my recommendation for understanding this stuff, guys. Again, if you guys like the way I teach, like the way I code, like this material that I'm putting up, please hit the subscribe button. Help me grow this channel. I'm looking forward to helping you guys learn. And like I said, there's lots of material on the way. Thanks for watching. Peace out, everybody.